Howdy folks, welcome back to another CS128 honors lesson. Today, we'll be continuing our discussion on parallelism and concurrency with a specific focus on threads, ownership, and how they interact. So our goals for today is first to review a little bit, then we'll discuss thread ownership, the move keyword when it comes to threads, and then some code examples will prompt us towards why messaging is important or why communication is important and how messaging specifically can help with this. So without further ado, we'll go ahead and get started. Some quick reminders, MP3 releases today. This is your last MP, so congratulations for almost making it to the end. MP2 is due tomorrow, and homework 8 is due tonight. Let us know if you need an extension. Homework 9 and homework 10 will release today. Apologies for releasing homework 9 a little bit late. It was supposed to release on Tuesday. Both of these will be due 3/11 to give you all some extra time, so hopefully that helps a little bit. And I believe right after that is spring break. So, okay, we don't really have any homework over spring break. Technically, there will be 2 homeworks released during that time, but you don't have to work on them during spring break. We give you extra time. We pretend that spring break doesn't exist. Your unofficial homework over spring break is to find groups and to come up with project ideas. I'll discuss more of this in some of the upcoming lessons, so keep an eye out for that. But okay, we'll also release some documents and whatnot for y'all to reference on what we look at. Really, the big thing that we want is for whatever project you do to be something that you're proud of. So historically, these projects have been things that you create sort of from the ground up. And we look for you to sort of be using advanced concepts, to be writing good Rust code, for it to be something impressive and something that you're proud of. But I think, for example, someone brought up the idea of contributing to open source software as their final project. We love that. I mean, that's a really, really cool project idea. And so if y'all can come up with something like that, then, of course, let us know and we'll probably be more than happy to allow it. We really encourage you to use external packages during the final projects. So, write Rust like a normal human would in a normal development environment. You don't have to do everything from scratch. We don't really expect you to. There's a ton of cool packages out there that can help, and we'll start highlighting some of these in some of the future lectures to give you some ideas of just the possibilities that you can work with. So keep an eye out for that as well. But without further ado, we'll go ahead and get started. Did I already say that? I don't know. Some quick review. So, when we want to spawn a thread in Rust, we need to first import the std thread. Of course, you don't actually have to. You could use std : thread every time, but to save ourselves some syntax, it's probably better to do that. Oops. So the alternative is to do std : thread every time, but, keep yourself sane. When we want to spawn a thread, all we need to do is call thread spawn. Thread spawn takes a closure. A closure represents the code that thread should execute. Closures are anonymous functions that capture their environment. Anonymous meaning there's no name for this closure, though there could be. And then I guess it would become a function, right? And then by capture their environment, it means, any local variables defined here, any functions defined up here, this closure sees and has access to, potentially. And we'll look at a quick example of that in just a bit. Okay, thread spawn returns a handle, which we can use eventually to ensure that this thread has completed execution. And then, of course, our main thread also is going to continue execution. It spawns other threads, but it can keep doing things in the meantime. And so in this specific example, our spawn thread will print 1, 2, all the way to 9, waiting 1 millisecond in between each. And our main thread will first spawn a thread, which takes just a little bit of time. And then it will print 1, 2, 3, 4, waiting 1 millisecond in between each. And then it will wait for the spawn thread to finish. Apologies for the mouse handwriting. I know it's not the best today. And so, one thing that to keep in mind is we don't actually know when these things are going to execute. So, we could, for example, get 1, 2, 3, 4 from the main thread. And then, 1, 2, 3, 4, 5, 6, 7, 8, 9 from the spawn thread. Or it could be the other way around. All of the spawn thread could finish before the main thread continues execution at all. Or it could be, some combination. So we could get, 1, 1, 2, 2, 3, 3, 4, 4, 5, 6, 7, 8, 9, or something, something else. We don't know when these things are going to happen, but, that's fine because it allows us to sort of do things at the same time, concurrently. Okay, so let's start to analyze a little bit how ownership works. It's very common that these threads require some parameter that we have in the main thread, right? We need to assign some work to this thread and eventually receive work back. And so how do we actually do this? So this is a quick code example, and I encourage you all to read this and analyze what happens. Does this work? Does this error out? What do we think? Okay, so in this specific case, this actually doesn't compile. And the reason for this is because we don't know the lifetime of A. A could theoretically go out of scope before we call handle join, right? Before we have an assurance that this thread has finish, A could go out of scope. And so let's analyze what's happening here. Theoretically, we enter some scope and we define A, and this closure will capture its environment. So it says, hey, I need A, let me grab a, whoops. Geez. Okay, let me grab a reference to A, because I only need a reference for println. But then A goes out of scope and the value is dropped. But this thread has not finished executing yet. And so then if this thread decided to execute, it's going to have a reference to a value that has been dropped, and your computer would explode. So there's two major ways to fix this. The first way is to define the lifetime. This is possible in Rust, and we'll learn about this in the future. But for now, the syntax for defining lifetimes is a little bit clunky and a little bit annoying. And so two, the much easier way, is just to give the... My mouse handwriting today is so rough, I apologize. Let me see if the trackpad's going to be any better. It's not. Oh, geez. Okay, the second option is to just move ownership of A into the thread. So we don't need access to A after this, and so we can just give this to the thread, and it'll determine when to drop it. And of course, we do this with the move keyword. And so it's very easy. All we have to do is precede our closure by the move keyword, saying, hey, I know you only need a reference to A, but why don't you just take the entirety of A? Take ownership of A. And this code works. This code compiles. It does exactly what you would expect it to do. Of course, just keep in mind, we don't have access to A anymore here. So we have to be a little bit careful. Okay, let's do a quick example. So it's a very common operation in computer science that you have some array of values, and you would like to, we'll say, sum up all of the numbers in this array. Okay, so let's just say, for example, these are all ones. The single-threaded approach is pretty straightforward. All we have to do is say, okay, let sum equal 0, and then iterate over each element. So 1, and then 2, and then 3, 4, 5, 6, until we get to the end. Our alternative, if we want this to be multi-threaded, is, okay, there's many options. One option is to treat this array as a couple contiguous chunks, right? Break the problem into smaller parts. And then we can assign each of these chunks to its own thread, and they will compute some value, which is the sum of its own chunk. And then all we have to do is sum these three values together to get the final answer, right? So let's do this. Okay, wonderful. Okay, yeah, this should be capturing everything. It looks good to me. Okay, so the first thing that we're going to do is use std thread because I want to save myself keystrokes. Now let's start by creating this vector. When we want to create a vector, we can remember that the syntax is vec of data, comma, length. And so let's just say let data equal some vec. And we want a vector of vectors, so we'll do that for now. And how many do we want? Well, one for each thread. Okay, apologies, this should be a semicolon. And let's define num threads real quick. So const num threads, usize, we'll just say is 16. Powers of 2 are nice. Okay, and then this inner vector we'll just say is 1, and it'll be chunk size. Okay, once again, const chunk size usize equals, I don't know, 32. Wonderful. Okay, so let's analyze how we can do this. The normal way we would approach this is to say something like let handle equal thread spawn. Sure, we'll move. And then really, okay, all we'll worry about for now is passing this chunk into it. So we'll do this, debug syntax, because it's a vector, chunk. Okay, well, this is kind of tough, right? Because ideally we want to be able to change the number of threads. Maybe on your machine you have 8 cores, and so we want this to be 8. On my machine I have 16. On someone else's machine it's 32, or we're running it on a supercomputer and it should be 128, right? What was it, 16? I don't know. So we can't really do this, right? We could like copy each time, and then we have to make sure all of the handles are ending, so we have to name all of these something different. But of course, if we have the move keyword here, okay, if we say something like, let's just say this is like data 0, and this is like data 1, this is already moving data into this thread. And so we actually don't have ownership to move it into this thread. Okay. Okay, but we could do something like, okay, let chunk 1, chunk 0 equal data of 0. And then we can only pass this chunk into this, which maybe helps. Okay, clearly this is not necessarily the best approach, right? We'll worry about this issue of getting the data back later, but this is clearly not the best. One of the sort of interesting parts that I think surprised me when I first learned it is there's nothing stopping us from spawning threads in something like a for loop. So we can say for chunk in data, and let's spawn some thread. And we'll move. Why are we moving? Well, okay, we don't need access to this chunk at all anymore. And we will once again println. We'll do debug syntax because it's a vector, and we'll print chunk. Okay. This needs a semicolon, and then, okay, for now, let's just worry about getting this to each thread. So what happens here? Okay, clearly this is not the most efficient approach, and this isn't necessarily solving our task yet. But there's sort of two major issues. Okay, first of all, let's just run this and make sure that it works. Wonderful. Okay, so each thread is getting the correct thing. This should be a semicolon. Thought I fixed that. Okay, so each thread is getting 32 ones, which is what we want to see, which is nice. We can chain this to something like, 4, and then each thread will get 4 threads, or there will be 4 threads. We can change it to something like 128. And okay, there's 128 of these. Good luck counting. Okay. So we're moving ownership into this, so this is good, but it's still not perfect. Notably, there's this issue of getting it back, right? There's this issue of, okay, if we even perform a sum, so let's just say sum equals chunk, oops, iter, making a lot of typos, dot sum. Okay, so we'll sum the chunk, but how do we get this back? Okay, so let's brainstorm for a moment here. One approach is maybe have some mutable variable that we pass into it, right? So we can say something like let mut total equal 0. Okay, of course, we could do this, total plus equals sum. Great, okay, does this work? I mean, not really, right? This doesn't quite work, because the moment we use total, we're giving ownership of total into some thread, and a future thread needs it. So that won't quite work, right? Additionally, there's the fact that we don't know when these threads are going to execute. And so this total plus equals sum really can be let temp equal total, and then temp plus equals, or temp equals temp plus sum, and then like total equals temp. Okay, this is a little bit more steps than necessary, but the important part is one thread can do this step, and then another thread could change total. And so this isn't really memory safe, right? And this now reintroduces all these ideas that we already saw in yesterday's lesson. Okay, we can put a mutex on it and restrict access. Some threads are more important than others. We assign priority. Okay, none of those are really going to be the right approach here. Those are going to be way too much work. We've already analyzed it, though they are sort of a valuable approaches nonetheless. One thing that I want you all to realize is we discussed very briefly at the end that there's two major ways of communication. The first way is shared memory, and then the second way is messaging. When we have some in like this, right, some shared thing, let's even make it a box because I think that would be more appropriate to begin with, right? Obviously, it needs to probably live on the heap. When we have something like this is shared memory. We have multiple threads all accessing the same piece of memory, right? And shared memory is fine, but when you do shared memory, you have to keep in mind these issues of, who's editing what when, right? And we'll analyze shared memory in probably, I can't remember if it's next lesson or the one after, but we'll analyze shared memory and how to solve this exact problem with shared memory. But for now, I actually want to introduce you to a different approach, which is messaging. So what does messaging mean? What does it mean to pass messages? Rather than sharing memory, each thread is going to have their own data, and they can communicate across a channel. Okay, and this channel is sort of a keyword here. Channels have transmitters and receivers, and a channel is closed if either one is dropped. Generally speaking, they have a receiver and multiple transmitters. And specifically, okay, you can do other types of communication, but the one that we're going to look at is called MPSC, or multiple producer, single consumer. Okay, and to visualize this, think of a river, right? This is, I think, a popular analogy. And every time we spawn a thread, we're putting people upstream that can drop messages into the river, and then downstream we have someone who's reading all of the messages as they come in, first out, right? FIFO. Okay. Of course, this can just be, in this example, one person dropping things into a river and one receiver. Okay, and let's analyze what's happening here. So we create our MPSC channel, we create our river. It has a single transmitter and a single receiver, TX, RX. We then spawn some thread, and we want to move all of the things that we use into this. And we will send some string that says hi from the transmitter. So we send hi. And then down here, we will wait to receive a single value. And when we receive a single value, we will unwrap it. And then we will print it. Okay, so couple things to analyze here. First, where are all these unwraps coming from? Well, many things can fail, right? We can have, these are all going to be result types. Generally, it's going to succeed. And if it does fail, we probably want to error. But, tx.send is going to return a result type. And rx.receive is going to return a result type. Because what if this thread throws an error and then we're going to get an error here? Bad things might happen. There's cases where you might want to handle those errors and not end execution. In this case, we just immediately unwrap, and so we would end execution if some error occurs, which is fine. Whoops. Okay. And so what we do is we send some value down the stream, and eventually we're waiting here to receive it, and we get hi, and we print it. And that's it, right? That's really the magic here. Now, what happens if we add this line? What happens if in the thread we attempt to print it? Okay. Hopefully not too surprisingly, this is not allowed. We've transferred ownership in this step. We no longer own val, right? Val has been given to the main thread, and so we can't print it. So, just keep in mind, if you do send something, you can't get it back. Okay. And then additionally, you can send multiple things. So once again, we'll say create our channel, txrx, and then our tx will say, okay, create some vector hi from the thread, and one at a time, it will send, hi from the thread. Remember, this is first in, first out, so these will arrive in this order, and one at a time, we will receive them. Okay, and I have a question for you all, which is, when do we know to stop this for loop? So take a moment, pause, or just think about it, and analyze when do we know, when should our main thread continue past this for loop? Or how does it know the length of this for loop, right? We receive some value, but it's not like we're passing the length of this vector. And we're not passing the length of this for loop, right? It only knows that it's sort of receiving messages or not. So how does it know when to stop? Okay, this is actually a question that we're not going to answer right now. We're going to answer in a little bit, just because I think that it's fun to ponder for a bit. Okay, and then similarly, we did call this multiple producer, so we can have multiple transmitters. So in this situation, we have a river, just for fun, I'll increase the quality of my graphics. Okay, still we only have one receiver in this case, so Rx, but we have a transmitter here, we have a transmitter here, and let's analyze what these are doing. So we will clone our transmitter. I'll call this TX1. That's how you sort of pass multiple things, or how you can have multiple transmitters just by cloning. We'll spawn one thread. This thread will use TX1, and it will send hi from the thread. Okay, so hi from, or rather opposite order, hi from the thread. We'll create a second thread, and this one will say more messages for you. More messages for you. And again, we wait 1 second between each. And then our receiver, once again, will for loop, waiting for each of these messages and printing them out as they arrive. Now, a couple questions. Do we have any idea the order that these are going to arrive in? Yes and no, right? Yes, we know that we are going to get hi before from, before thread. And we know we're going to get more before messages, before you. But we don't know the relative order, right? We could get more messages, hi, for, from the you thread, right? And we just have no guarantee over this. But we know that the relative order will be the same. And so it's okay. And once again, this question raises, when do we know to stop the for loop? We'll analyze that shortly. But okay, this is how you do multiple threads. And this is really what we need for our problem is, okay, let's change this a little bit. We calculate some sum and then send the sum, and then, sum equals 0, sum plus equals received, and like we're done. Okay, really bad mouse handwriting, but life goes on. So let's return to our example now with messaging. Okay, we know that we want to create some messaging thread. So use std sync MPSC. Okay, and let's, instead of this box garbage, let's do this. Let's say let txrx equal MPSC channel. Okay, and for now, we're actually going to ignore the threads ending. Okay, and we'll analyze why we can do this in a little bit, but just stay with me for now. Okay, let's say let tx thread equal tx.clone, and then we will send tx thread.send our sum. Of course, we need to unwrap, or we should unwrap. I think you actually don't need to. Wonderful. Let's build our receiver on the other end. So let mut sum equal 0 for received in our receiver. So for each message our receiver receives, we'll say sum plus equal received. And then let's print a couple things too. We'll print ln, just for debugging's sake. We will print received total, received sum. Looks good. And then at the very end, of course, we want to print what we have. Total is, and we'll print sum. Okay, this looks good to me. There's a couple bugs or some warnings, potentially errors, that I think we'll be faced with in just a moment. But let's cargo run, see what happens. Okay, so first thing is sum not, oh, whoops. And then what's the other thing? Yeah, okay, that's it for now. Okay, so a couple things. Did it save? Why is it still yelling at me for that? Okay, a couple things. It doesn't know the type that we're receiving, and so we do need to type this. Now, this one's pretty easy to fix, but a little annoying. We'll just make sure that we type sum, and the way we can do this is just saying like, okay, make this usize, and we'll make sure that it knows this is a usize. That should be fine, right? We'll also type this just to be extra safe. Oops. Okay, so it knows that it's doing a sum on a usize, it's writing a usize, it's adding to a usize, and life is good. Okay, and we get some warning, but let's look at what we print. So these 3 threads are spawned, or I guess 4 threads are spawned, and we start adding together, which is good. And then it looks like we spawn like the other however many threads, and that's good. And we receive the messages from each, and they're all correct. They're all 32. But if you're careful, you'll notice that we're actually not getting to this line. Okay? And so this comes back to that question of how do we know when the for loop ends? And of course, maybe it shouldn't be too surprising, but we know the for loop ends when all of the transmitters have been dropped. And so my question to you is, have all of the transmitters been dropped? Let's analyze it. Okay? Well, every time we clone a transmitter, we drop it when the thread ends. So those are all being closed. But there's still the TX, the original transmitter. And this is not getting dropped. This still lives here. And so we need to manually drop it. And ideally, or luckily, it's pretty easy to manually drop things. You just say drop. Okay, so we can close this, and it's going to yell at us for a ton of things. We can run it again, and we will get total is 512. Life is good. We can change these. Let's make this. Let's make 128 threads with each one doing 128 numbers. This is going to spam my console, but it finishes in record time. I encourage some of you maybe benchmark this. I'm not quite sure if this specific approach will be faster with threads. I think if it is going to be faster or slower, it's going to be highly dependent on chuck size because of caching. But this is my computer engineer coming out rather than my computer scientist coming out. But okay, wonderful. So we now have this great example. We're spawning multiple threads. We're iterating between them. I just noticed that this was in the way. Let me fix that. Apologies. Okay, so sorry about that. This was in the way. Hopefully you all can see now. I'm not sure how much it was blocking, but okay, that's pretty much it. So next lesson we'll continue our discussion on parallelism. But I think that right now we've sort of learned a very, very powerful amount, and some of these examples should also help for your MPs. So see you all around. Let me know if you have any questions, and bye-bye.